Hey everyone, welcome back to Matthew 61. This is Scott. Let's get started. So today we are going to be turning the page on a new chapter. We're going to be starting chapter 2, where what we'll be talking about is more of the matrix side of things, and in particular matrix multiplication type things, as opposed to more vector or row reducing type things. So 2.1 starts us off with a discussion of matrix operations. Now, matrix operations, so on the one hand, those include all of the normal things that you're used to from vectors. In particular, we can do scalar multiplication, and we can do matrix addition, provided that they are of the same size. So first off, let's discuss our setup. So our setup, say A is an M by N matrix. And just to remind you, the M here refers to the number of rows. So the first, so whenever we're giving the dimensions of a matrix, the first number is the number of rows, and the second number is the number of columns. And again, just to remind you, rows oriented that way, columns oriented that way. Okay, so then scalar multiplication and matrix addition all happen the way you would think. So then scalar multiplication, you just scale up all the entries of A accordingly. So scale all the entries of A by the factor. So for example, let's say we had A equals, let's say we'll have a 2 by 3 matrix, 1, 2, 3, 4, 5, 6. Then something like, say, 3A would be 3 times 1, 2, 3, 4, 5, 6, which would then just equal 3, 6, 9, 12, 15, 18. So it would just scale accordingly. And notice this is exactly the same process as vector scalar multiplication. So if you were to multiply a vector by a scalar, you would do that the same way as you would do a matrix. Similarly, we can add matrices, provided they are of the same dimensions, and it would also correspond with how you do it for vectors. So matrix addition. So if A and B are both M by N, so they have to have the same configuration. We can add them component-wise. So for example, let's say that A was 1, 2, 3, 4, 5, 6. Let's say B was equal to -2, 1, 6, 3, -4, and 0. It's important that they have the same number of rows and the same number of columns, otherwise addition is not defined. But if it is defined, then we just go entry by entry. So A plus B would be just 1 plus -2, 2 plus 1, 3 plus 6, 4 plus 3, 5 plus -4, 6 plus 0. And so you would just get what you would get. -1, 3, 9, 7, 1, 6. Again, only defined if they are the same number of columns and the same number of rows. So for notation, what we can say is this. So Aij, this represents the entry of A, of capital A, in the ith row and the jth column. So this is the entry of A in row I, column J, and then similarly for B. And then if I wrote something like A plus B, Ij, that would mean the same thing. And column J. So the notation here is if it's just a matrix you're talking about, you just use the lowercase version of that letter with I and J as subscripts, and then if you're talking about something more complicated, you just put brackets around it and then do a little subscript I, J. So then we would write A plus B sub ij to indicate the ijth entry of the sum is just the ijth entry of A plus the ijth entry of B. Okay, now for matrix multiplication, what we want to do is we want to first describe when we can and can't do it, and then describe how we would do it when we can. Matrix multiplication. So first off, the setup. AB is only defined if A, or let's put it this way, if the number of columns of A is the same as the number of rows of B. So for example, if A is m by n, then B has to be n by something. We can say n by p. The usual convention on this is we pick letters towards the middle of the alphabet for numbers of things. So L, M, N, P. We tend to skip O because it's a little ambiguous. It looks like a 0. So these must match. and in particular m by n, n by p, these have to be the same. And the result will be m by p, so Mike by Papa. So Mike by November times November by Papa makes a Mike by Papa matrix. So the result would be m by p. Now to actually generate the result, let's take a little interlude and describe or perhaps remind you what dot products are. So interruption, so the dot product of vectors. So there are a couple different ways of formulating the dot product, and the one that is useful to us right here is the entry by entry version of it. So not the cosine version, but the entry by entry version. So the dot product of vectors, you can find that by just taking something like this. So let's say that v is equal to a, b, c, and then let's say w is equal to d, e, f. Then v dot w would be the number that you get. So a scalar, so that's why it's called a scalar product sometimes. A, D plus B, E plus C, F. So you add the product of corresponding entries and you add the result. Then the entry in row I, column J, oops, sorry, it's a sunny day, my brain is melting. Column J of the product A, B will be the dot product of the ith row of A and the jth row, sorry, jth column of B. So in other words, in AB, we have row, 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 times column, 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 and it's going to be row dot column all through. And each row of the one with each column of the other. So for example, let's say that A was 2 rows. 1, 2, 3, -4, 5, 7. And then B So let's say 2 rows, 3 columns. So then whatever I know about B is its number of rows must be 3, and its number of columns can be anything. So its number of, so it must have 3 rows, and it can have any number of columns. Let's say that its number of columns is just 2. So then what we're going to have would be, let's say, going down, counting down 0, 1, 4, -2, 8, and 1. So then, if we go rows to columns for AB, so AB would be, so for the very first entry, what we're going to have is row 1, column 1. So that's going to be 1.0 plus 2.1, or times really, plus 3 times 4. So that's going to be entry number 1. Then we're going to have, for the next one, we're going to have first row, second column. So 1 times -2 plus 2 times 8 plus 3 times 1. And then we're going to have -4 times 0. First we went that with that to produce that, and so on. Okay, so -4 times 0 plus 5 times 1 plus 7 times 4. And then we have -4 times -2 plus 5 times 8 plus 7 times 1. So then this is going to equal, so 0 plus 2 is 2, plus 12 is 14. Here we're going to have -2 plus 16 is 14, plus 3 is 17. Here we're going to have 0 plus 5. So we're going to have, so 0 plus 5 is 5, plus 28 is 33. And then here we're going to have 16 plus 40 is 8 plus 40 is 48, plus 7 is 55. And you'll notice that this 2 by 3 times this 3 by 2 resulted in a 2 by 2 matrix. The middle two had to match, and then the outer two gave the dimensions of the product. Now, what if I decided to reverse things and do B times A? So then B times A is now going to be 0, 1, 4, -2, 8, 1, 1, 2, 3, -4, 5, 7. So now it's going to be a matter of matching rows of B with columns of A. So we always go rows to columns. Row.column. That's the philosophy. Row.column. Row.column. So this is the little indicator of which direction we're going. It's nice to always remember row with column, row with column. So then what we're going to have here is 0 times 1 plus -2 times -4. That'll be first row, first column to make the upper left entry. And then same thing, but the next column. So that's going to be 0 times 2 plus -2 times 5. And then third column, 0 times 3 plus -2 times 7. Then we repeat, but with the second row. So it's going to be 1 times 1 plus 8 times -4. And then here what we'll have is 1 times 2 plus 8 times 5. So looking at the second column. And then we'll have 1 times 3 plus 8 times 7. And then down here, what we'll have is 4 times 1 plus 1 times negative 4. And then right here, we're going to have 4 times 2 plus 1 times 5. And then we're going to have 4 times 3 plus 1 times 7. And notice when I've written it out like this in a very systematic fashion, you can tell what is the same and what is changing with each entry. So down this column, you'll notice the second factor is always the same. Down this row, you'll notice the first factors are always the same. And the other one will then change in correspondence to the other one will just change in correspondence to the corresponding row or column of either of the two products, all depending. So those two together made that. And then we get our answer, and notice it's going to be a 3 by 3 because this was a 3 by 2. This was a 2 by 3. So our 3 by 3 answer is going to be 0 plus 8 is 8. 0 plus negative 10 is negative 10. And 0 plus negative 14 is negative 14. 1 plus negative 32 is going to be negative 31. 2 plus 40 is going to be 42, and then 3 plus 56 is going to be 59. Again, if I make an arithmetic mistake that does not compromise the procedure, it just is an effect of sunshine. So 4 plus negative 4 is 0, and then here we've got 8 plus 5 is 13, and lastly we've got 12 plus 7 is 19. And so we got a 3 by 3 result that looks like this. Now, some important facts. So if we wanted to write out the actual formula for the product of matrices, we could do it as follows. So, formula for AB. So if we think about what the entries of the product will be, we can go entry by entry. In other words, just say IJ of the product. And if we look at what we took to make this, it was all of the entries of the first row. So this would be A11, A12, A13. And multiplied by the entries of the first column of B, and so that's going to be B B11, B21, B31. So the row of this is going to be determined by the sum. So it's going to be a sum, and it's going to be the sum of, and it's going to be for K, and the sum is going to be A, and the I is fixed, and the column is going to be changing, and then apologies there, the camera cut out for a second, and so here's what I wrote in the meantime while the camera was out. So I wrote the K was going from 1 up to N, so that's the number of columns of A, or the number of rows of B, and then it's A, and the entry of the A for a row is the same as the entry we're looking at here, The entry for A for a column is the part that's changing as we sum from 1 to n, and then times the B, which is going to be the kth row, so again, that's the index that's changing, and then the J is fixed, so the column is always staying the same. Now, this is a very abstract way of writing it, but this is a way that will perhaps make more sense to those of you who have a little bit more experience in coding. What this would be is actually it'd be a for loop, and essentially we would be saying that we would define, so actually it'd be like a triple for loop, so it'd be for I from 1 to m, for B, or sorry, for J from 1 to P, and then there would be for K from 1 to N, we would do entry I K from A times entry KJ for B. Now, the reason why we wrote this is not because I expect you to think of it in these terms. I don't expect this to make a whole lot of sense to you, frankly. You saw the sum in maybe a statistics class, or you've seen it certainly in Calculus 2, when we're doing the Riemann sums and things like that. But it's not exactly what I would call your native language. The reason why we wrote this is so that when it comes to certain other properties, we'll be able to spot things that are in fact the same. So, now, let's make a few notes about some of the important elements of matrix multiplication. So for one thing, matrix multiplication, unlike the multiplication of regular real numbers, is not, as they say, commutative. So what that means is AB is absolutely not guaranteed to be the same thing as BA. Every once in a while, this might happen to be the case, but it is certainly not guaranteed the way it is with numbers. And in fact, if AB is defined, that doesn't even necessarily mean that BA is defined. So these might not even both be defined, let alone both be equal. So matrix multiplication is not commutative. Also, if we know that AB is equal to AC, it does not necessarily follow that B equals C. So if we were talking about numbers here, and I knew that A times B equaled A times C, I could basically just divide both sides by A, and then that would give us a chance to see that B equaled C. That's a very common step that we do. That's basically what happens whenever you divide both sides of an equation by something. However, that is not the case for matrices. It does not follow that if the products are the same and they have the same first factor, that the second factor is also the same. So that's also not true. And furthermore, the zero product property, or zero product principle, as it's called frequently in algebra, is also not true here. So if AB equals 0, it does not follow, I guess again, if AB equals 0, it does not follow necessarily follow that A equals 0 or B equals 0. They could both be non-zero, and the product could still equal 0. So if you recall, back when we were first dealing with algebra, This was the key to solving things that could be factored. If you could factor it, then you could tell that if the product was going to equal 0, one of the two factors must have equaled 0. That is also not the case here. So what this means is most of the rules of algebra are going to require a little bit of careful handling if we want to use them for matrices. However, there are certain properties that do carry over. The reason we call it multiplication is because it does have some of the other properties that multiplication has for numbers. So here are some properties. And for these, assume the sizes are compatible. Assume compatible sizes. So every time there's a multiplication or an addition, assume that the correct things match. So for the first property, what we have is this. So A times BC is equal to AB times C. Now what this means is that multiplication of matrices is associative the same way it is for numbers. So what this means really is if we have a chain of factors we can combine adjacent ones either from the left or from the right. So we can basically do a multiplication and then do the result and then multiply the result by another matrix, and it will make sense and it will be well defined whichever way we work, whether we work from the right to and work our way leftward, or work from the left to and work our way rightward. Also, matrix multiplication is distributive. So that means that if we have A times B plus C, that is the same as AB plus AC. So this is good news. It means that a lot of the properties that have to do with polynomials and things like that, we can actually continue to make use of. We can also distribute in the other direction. It is also the case that if we have A plus B times C, that's the same as AC plus BC. Now, an important thing here is I am not at liberty to ever reverse the order of any two factors. So this is a thing that is that you can be a little loosey-goosey with when we're talking about numbers, but when we're talking about matrices, you have to be very careful to always preserve the order of the factors. So notice that if A came first and B came second, even if I'm distributing it, A still comes first, B still comes second. A first, C second, A first, C second. And same thing over here. You cannot reverse the orders of the factors, but you can distribute them. Let's see, now furthermore, if we do scalar multiplication, that will work in the proper way. So if I do a scalar multiple of A times B, this can be associated in either of the following two ways. We can do RA, so just do the scalar multiple on the A times the B, or I can do A times RB. So I can put the scalar multiple into either of the other two factors, and that'd be the same as having the scalar multiple out front, where R is a scalar. This would not be true if R here were supposed to be standing for a matrix, And the reason why it would not be true, so this part would not be wrong, but this part would be. We cannot assume that we can reverse the order of the A and the R. That's what would be wrong about this if R were a matrix rather than a scalar. And then finally, the fifth property here is if we have the appropriately sized identity. So I, A, and here I'll put I am A, is the same as A, which is the same in turn as A, I, N. So remember, this is from section 1.9, so the previous section. These are the M by M identity matrix and N by N identity matrix. So that means that the identity matrix really does function the way the multiplicative identity ought to for numbers. So it behaves the way a 1 behaves. All right. Now, as long as A is a square matrix, that means that it can be multiplied by itself. If it's not a square matrix, if it is not M by M or N by N, it cannot be assumed to be multiplied by itself because it won't line up. But if A is square, then we can multiply it by itself. And we can multiply it by itself over and over and over again. So powers. If A is square, in other words, N by N, so same number of rows and columns, then we can define exponents. So we can say A to the 0, that's just going to be the identity matrix. It would be the N by N in this case. A to the 1 would just be A. So notice these are just like with numbers. And then other than that, A to the K is equal to A times itself, K times. I guess technically that's also true for the 1, but K copies. Alright, and then the last concept of this section is the transpose of a matrix. So the transpose of a matrix is what you get if you interchange the rows with the columns. So you basically take the matrix and you turn it around, turn it on its head. So transpose of a matrix. So AT, so you put a little superscript T, capital T. So this is the result of interchanging the rows and columns of A. So for example, if A is equal to 1, 2, 3, 4, 5, 6, A transpose would be 1, 2, 3 as the first column, 4, 5, 6 as the second column. So what was the first row becomes the first column. What was the first column becomes the first row, and vice versa. and so on throughout all the elements. So if I wanted to write this as a formula, so A transpose ij is the same as A ji. It just reverses the indices. Now, let's talk about some interesting properties of the transpose. And this will be the last item on the agenda. Properties of transposes. So again, assuming everything is defined here, we have compatible sizes. So the first property of a transpose that is of interest to us is what happens if you take the transpose of the transpose? So the first transpose turns the whole matrix on its side. Row becomes column, column becomes a row. Then, if you're taking that and you take the transpose, what happens? Well, what is now a row becomes again a column. And what is now a column becomes again a row. So taking a transpose of a transpose takes you back to where you started. So the transpose done twice undoes itself. A transpose of a transpose gets you back to the original matrix. Now, what if you were to add together two matrices and then take the transpose of the result? Well, that's the same as adding entry by entry, and these are all the same entries, they're just all scrambled around. And the way they're scrambled around is that the result will be A transpose plus B transpose. And the third property here is that the scalar multiple RA, if you were to take a transpose of that, that's the same as just R times A transpose. Now from all this, you might think that the transpose has no surprises in store for us. However, there is a property of transposes relating to the product that will hold a lurking danger here. So let's say A and B have compatible sizes to be multiplied, and we take the transpose of the product. Now, based on property 2, for example, you might expect and you might have hoped that that this would be A transpose, B transpose. However, that's not the case. So before we even write that, let's just think of this. If A is m by n, and B is n by p, then A transpose would be n by m, since every row becomes a column, every column becomes a row, and B transpose would be p by n, and so A transpose B transpose wouldn't even make sense because we would have a mismatch in the middle two dimensions. However, if we reverse the order, then it would make sense. So then we can do B transpose A transpose. So this is like a kind of the equivalent of what you might do in a physics or an engineering class of dimensional analysis, just trying to figure out which direction even makes sense as far as the dimensions of things. But now let's try to make sense out of this in general. So thinking about the actual definition of the transpose, so you don't have to write this down, but I just wanted to bring it up. So if we think about the definition of the transpose, you can think of it in a couple ways. You can think of it as a dot product, or you can think of it as this sum. Now, if what we're thinking of it as is a dot product, we're taking the dot product of row of A with column of B. Now, if we want to reverse the roles of rows and columns in the product, we can get those same answers by taking the dot products of the rows of B transpose, which are the same as the columns of B, and the columns of A transpose, which are the same as the rows of A. So then what that would amount to here, if we were writing it like this, is I and J would be completely switching roles, and we would be talking about the ijth entry would be AJ B I, and those would then in turn correspond with the rows or columns of the transposes. But I don't want to get into that too crazily. Let's just see it with a quick example, just to make sure that it makes sense. And in the example, we can watch the numbers do what they're supposed to do, and watch it all work out. So let's take A to B, our old friend, 1, 2, 3, 4, 5, 6, and we'll take B to be 1, 3, 7, negative 2, 2, 2. Alright, so if I did A, B, that's going to just be row. Here, I want to once again write it just because we need practice. 1, 2, 3, 4, 5, 6. 1, 3, 7, negative 2, 2, 2. And the key mystical symbol here is row dot column. So row and column make the first row column. So 1 times 1 plus 2 times 3 plus 3 times 7. And then 1 times negative 2 plus 2 times 2 plus 3 times 2. And then here, basically all of those first factors all become 4, 5, and 6 instead of 1, 2, and 3. So 4 times 1 plus 5 times 3 plus 6 times 7. And same thing right here. 4 times negative 2 plus 5 times 2 plus 3 times, plus 6 times 2. 6 times 2. Okay, so then that's what we will get right here, and then that's going to be 1 plus 6 is 7, plus 21 is 28. And then here we're going to have negative 2 plus 4 is 2, plus 6 is 8. And then over here we're going to have so negative 2 plus 4 plus, yep, okay. And over here we're going to have 4 plus 15 is 19, plus 42 is going to be 61. Let's see, so 42 plus 15 is 57. Yep. And then minus 8 plus 10 is going to be 2, plus 12 is 14. So this is the product of the two matrices, and then if we wanted to do the transpose of that, so AB transpose, that would be the same as just taking the first column and turning it into the first row, and vice versa. So 28, 61, 8, 14. Now let's think about what it would be like if we were considering B transpose A transpose. So this should end up matching that. So B transpose A transpose. So B transpose is take 1, 3, 7 for the first row instead of the first column, negative 2, 2, 2 for the second row instead of the second column, times 1, 2, 3 for the first column instead of the first row, and 4, 5, 6 for the second column instead of the second row. And now if we were to actually put the pieces together in proper matrix product form, we'll notice that we are getting 1 times 1 plus 3 times 2 plus 7 times 3. Interesting. I feel a sense of deja vu here. I feel like I've seen all of these numbers before. The only difference is last time I saw them, the factors were in different orders. But other than that, they are the same numbers being multiplied and the same numbers being added. And similarly here, we're going to have down here, it's going to be 1 times 4 plus 3 times 5 plus 7 times... that's not right. That's not right, I was looking at the wrong thing. So, okay. That is all going to be up here. 1 times 4 plus 3 times 5 plus 7 times 6. And then down here, negative 2 times 1 plus 2 times 2 plus 2 times 3. And then over here, we're going to have negative 2 times 4 plus 2 times 5 plus 2 times 6. Now, all of these are things that we have found already, but when we found them before, they were just, these two were just in reversed position. But this is going to be a 28. This one is going to be the same as what this one was before. They're all the same factors. So that's going to be a 61. This one is going to be what this one was before. They're all the same factors, just reversed in order. So that's going to make an 8. And then this one is going to be the same as that one, which is going to be a 14. So in doing this, we saw that they did in fact match each other. But more importantly than seeing that it's true, we also saw why it's true. We get all of the same factors just in reverse order that we had before. So these two things had to match, and they do. And they match because they are the result of the same numbers times the same numbers, just in opposite orders, and the sums of those. And the fact that that it got a little scrambled up is because it's the transpose of the result, which corresponds to the product of the transposes of the original matrices. Okay, well that is how that goes, and that will conclude this lecture and this week and our first installment of Chapter 2. So I will see you again for the next episode of Math 261. Until then, bye.